Okay, so before break, we did 2 days on what were called sampling distributions. So we did 1 day on, sorry, I guess you can't see this. 1 day on, in general, what is a sampling distribution. We talked about different statistics, biased and unbiased. And then we looked more in depth at the sampling distribution for sample mean. What was important was you being able to figure out, is the distribution normal, finding the mean, finding the standard deviation, and then calculating some probabilities. Today what we'll do to add on is we'll talk about sample proportion. So 1 page you should have in the notes looks like this. And this is just, in general, what is a sampling distribution. Sampling distribution displays all possible samples and a certain statistic. So in one example, what we did is we considered a very small population of size 6, and we said we want to calculate the sample mean. And we took samples of size 2. So the way to find your sampling distribution, you look at every possible sample of size 2. What we cared about was the sample mean, and you put those then on a dot plot or in a table. So what's important to recognize is that every dot on the distribution represents an entire sample. So this would be a sample of size 2 with a sample mean of 2. Sample of size 2 with a sample mean of 3. So that represents 2 people. That is called our sampling distribution. And then over here, that's different from the population and the sample. Population, every dot is 1 individual. Sample, every dot is 1 individual. So that was a sampling distribution. Below was a different sampling distribution we looked at. This time, same population, but we looked at samples of size 3, and we calculated the maximum. So we looked at all the possible samples of size 3, there were 20 of them, and then every possible, or the maximum of all of those samples. And this is the sampling distribution. So every dot represents 3 people, and it was the maximum in that sample. The other thing we talked about is the biased and unbiased statistics. Unbiased statistic just means that if you took all of your X bars, for example, and you averaged them up, you would get the population mean. For variance down here, if we take all the sample variances and we average them all up, we get the population variance. The big ones, though, are sample mean and sample proportion. And if you remember, sample proportion is p-hat. Maximum, minimum, and standard deviation are biased. So standard deviation is biased because if I take all the sample standard deviations and I average them up, I am not going to get the population standard deviation. Practically, what that means to us is if we take a single sample and we calculate the standard deviation, probably not a very good estimate of the population standard deviation. If we took a whole bunch of samples over time, we're still not going to estimate the population standard deviation well. Either we will have a tendency to overestimate or underestimate. What I need you to know is which statistics are unbiased and which ones are biased. And then the general idea of what that means. Next thing we talked about. We took a look at sample mean in particular because sample mean is unbiased. So we said if we look at all of the X bars of a certain size, and we average them up, we're going to get the population mean. That's because sample mean is unbiased. Bless you. Bless you. If we take the standard deviation, it's going to be the standard deviation of the population over root n. That is the spread of the X bars. And then what was very important is when the distribution of X bar is normal. If the population is normal, X bar will be normal. If the population is not normal, though, as long as you take samples that are bigger than 30, the sampling distribution, or the distribution of X bar, is going to be normal because of the central limit theorem. And then I don't know if we have any on here. We did some examples. That was a brief overview. I think we probably need to do some examples, though, still together. So what I want you to do is you're going to have to go towards the back of the packet and find this page. This is page 16. Page 16. Okay, so unrealistically, we are going to look at a population of only 5 students. I don't know why these 5, but these 5 students. We're going to look at population of 5 students, and from those 5 students, you are given their grades and their quiz scores. What you will be doing is you will be doing questions 1 and 3, not question 2. Question 1 says a random sample of size 2 is to be selected without replacement from the population. We are going to construct the sampling distribution of the sample mean and display it in a dot plot. Okay, before I let you loose to start this one, or to continue, how would you start this? Based on what we just went through. Sample of size 2, looking at sample mean. Got nothing? Okay, well, I'll help you with this one then. We are going to look at every single possible sample of size 2. And in that sample, we need to calculate X bar. I will tell you that there are 10 of those samples. So one such sample would be if I chose Abigail and Bobby. If their quiz scores then are 10 and 5, the X bar for that sample would be 7.5. So I chose these 2 students, averaged out their quiz scores. So you're going to do that for the other 9 samples, and then display them in a dot plot. When you are done with that, you are going to take a look at number 3, which is going to be a similar idea but a different statistic. Okay, I want you right now to move your desks into your group and get started, please. There is my sampling distribution for number 1. So like we talked about, what you should have done, write out all 10 samples, write out the sample means. This table is just considered work, that's it. This is the sampling distribution, the dot plot. It's the summary of what happened in all the samples. Really, we should have a label, like X bar, because that's what all those dots represent. And then, fun fact, we're not actually going to do the calculation, but if we were to take all of those X bars and we were to average them up, we would get the population mean. And again, why we care about that is that X bar is unbiased. So in the long run, if we were to take a whole bunch of samples of size 2 and average them up, we would get the population mean. So that was the first one you had to do. Next one you had to do. Problem 3. Again, write out all your samples. Same 10 samples. This time, though, what we care about is what proportion in that sample are seniors. So out of these 2 people whose names I forgot, one of them was a senior. So the sample proportion is 1/2. This table is just work. It is not the sampling distribution. The sampling distribution as a table is the summary, so the possible values of the sample proportion. And then you either could have used frequency or relative frequency. You don't have to do both. This is the sampling distribution, not the individual work. And again, fun fact, if we were to take all of those p-hats, all of those sample proportions, and average them up, what would we get? Without actually doing the calculation. Well, I mean, you're kind of doing it. You get 0.4. 0.4, that's the population proportion of seniors. 2 out of the 5 people were seniors. So we already know that without doing the calculation. So hopefully that helped refresh our memory a little bit in terms of sampling distributions in general. That's the first thing that you have to be able to do. Any questions on that? No? We're good? Okay, we're going to do a little more review, and then we'll take our new notes for today. If you go to the next page. The other thing that we talked about is sampling distributions specifically for X bar. And again, the reason we do that is X bar is an unbiased statistic. X bar is generally used when we have numeric data. So we're going to do 2 problems and then we'll go on to the new notes. Starting with problem 6. A grinding machine in an auto parts plant prepares axles with a target diameter, 40.125 millimeters. The machine has some variability, so the standard deviation of the diameters is 0.002 millimeters. The machine operator inspects a random sample of 4 axles each hour for quality control purposes and records the sample mean diameter x bar. Assume the machine is working properly. A, identify the mean of the sampling distribution of x bar. You mind if I borrow this? Okay, if you take your formula sheet, we've done most of this stuff on the front. Sampling distributions is the whole back side. So if you go to the back, it's going to say sampling distributions. Top one is for proportion. That's not what we're doing. If you go to the middle table, it says sampling distributions for means. And then it has 1 population and 2. So what you're going to notice it says is that mu of x bar, or the mean of the sampling distribution, is equal to the mean of the population. Mean of the population we were given. So that tells us that the mean of x bar is 40.125 millimeters. Standard deviation is the next box over. It tells us that the standard deviation of x bar is the standard deviation of the population over root n. Standard deviation of the population, which we were given, is 0.002. We're taking samples of size 4. So our standard deviation then is 0.001 millimeters. What I want to make sure is that we understand what that 0.001 represents. Okay, that 0.001 is the standard deviation of the x bars. So if we were to take a whole bunch of samples of size 4, and calculate the mean for each one, those x bars would differ from the population mean by 0.001 in the long run. So writing that in a sentence is a little wordy, but hopefully we can get the point across. In the long run, if we calculate x bar for many samples of size 4, x bar would typically deviate from the center, which is 40.125 millimeters, by 0.001 millimeters. So it's just the normal definition or interpretation of standard deviation. The big difference being we're not looking at individual axles, we're looking at samples of size 4. So if we took 1,000 samples of size 4 and in every sample calculated x bar, 0.001 is the typical difference from the mean. Okay, do we know anything about the shape of x bar? No. If the population was normal, then we know x bar is normal. We don't have the population though, and we can't use the central limit theorem because our sample size is only 4. Okay, what I want us to do, we are going to skip problem 7, go to the next page, which is problem 8. This is the last one we're going to do together before we move on to some new stuff. An insurance company claims that in the entire population of homeowners, the mean annual loss from fire is mu equals $250, and the standard deviation of the loss is 5,000. The distribution of losses is strongly right skewed. Many policies have 0 loss, but a few have large losses. The company hopes to sell 1,000 of these policies for $300 each. Assuming that the company's claim is true, what is the probability that the mean loss from fire is greater than 300 for a simple random sample of 1,000 homeowners? Okay, here's what we're looking at. Key word here being mean. Sometimes it might say average. So we're looking for the probability that the average, in this case x bar, is greater than 300. Now, this is going to involve some type of distribution then. Either we're talking about a normal distribution or a binomial or a geometric or something like that. Well, one thing we know is that the mean of x bar is going to be equal to the mean of the population, which we were given $250. We know that the standard deviation of x bar is equal to the standard deviation of the population over root n. So that's 5,000 over the square root of 1,000, because we're taking a sample of 1,000 homeowners. So then we are told the population is skewed right, or right skewed. Does that mean that x bar has a skewed right distribution? Do we know anything about the shape of x bar? Okay. X bar here is normal because of the central limit theorem. Central limit theorem applies when your sample size is bigger than 30. Always 30. So in this case, we're taking a really big sample. It doesn't matter, the population is skewed right. Our sampling distribution will be normal. So then, summarizing all of that, we know that x bar has a normal distribution. The mean of x bar we know is 250. Standard deviation of x bar we know is 5,000 divided by the square root of 1,000. Come on in. No, this is perfect timing. Okay, so here's what I would like you to do. Normal distribution, you need a figure. I have a 2-minute meeting, so 5-minute meeting. I'm going to go to my meeting. What you're going to do, draw a figure, and then calculate this probability, please. You're going to need a calculator. And if you get to part B, that would be great too. Good luck. We'll go over it when I get back.
And don't.
Okay, if we look up here, here is my work and answer for part A. Should have gotten an answer of 0.38. And then this should have been our figure. So you should have a normal figure with the standard labels, numbers from the problem. Most common mistake is that people will use 5,000 as their standard deviation on the figure. If you do that, even if you get 0.38 right, you're not going to get your credit. So I think we've talked about this before on the AP test. If you write one thing that's right and one thing that's wrong to answer the same question, it's going to be wrong. So, sorry. And then we should have shaded. Did anybody talk about or think about why that probability matters? It's not just a random probability. So what is the meaning of a probability that the mean is greater than 300? Why does that matter to the company? Nicole? They're going to be losing money. Okay, this does not mean 38% of the time they're losing money. It does not mean that 38% of the insurance claims are losing money. What it means is if we look at 1,000 homeowners a whole bunch of times, 38% of the time the company is losing money. Getting a lot of support back there? What's just going on? And here we go for part B. Part B, you do not need to define x bar again. You already defined x bar. I did it in green above. You do need a figure though again. I was pretty lazy on my figure. At a minimum though, on your figure, you either need 0.9 or 0.1 because that shows what you put in the calculator. This is an inverse norm question. That is not part of your work. Please don't write that. I just wrote that to maybe be helpful to you. Answer is about $452. How'd this one go for us? Went okay? Do we have any questions for me before we move on to new stuff? Okay, that was the stuff we'd already learned. That was probably buried a little bit, and hopefully that brought it back. Here is the page I now need you to find. This one. These are our notes. This is page 12. We're going to be taking notes for a little bit. By that, I mean about 2 minutes. And then we're going to do some examples. If you are comfortable where you are, great. If your desk is moved in an uncomfortable position, then swing around, please. Okay. The entire basis of second semester is sampling distributions for sample mean, x bar, and sampling distributions for sample proportion. Mean is calculated for numeric data, proportion is calculated for categorical data. So a few things I want to review real quick. First one, P, is the symbol for population proportion. P hat is the symbol for sample proportion. Some more vocab to remind us of that we did before break. Anything that comes from a population is called a parameter. So any number that comes from a population is called a parameter. Any number that comes from a sample is called a statistic. So then there's only 3 things you have to know about p hat. With sample mean, we talked about center, spread, shape. Talk about the same thing. So first property you need to know. If we take all of our p hats and we average them up, we're going to get the population proportion. This is on your formula sheet. This one's at the top. So we already talked about mean. At the top is proportion, and we have 1 proportion and 2 proportions. So that is on there. That is the center part. For spread, if we take all of those p hats and we find the spread of them, that's going to be the square root of p times 1 minus p all over n. Again, that's on the formula sheet. You don't need to memorize that. And then lastly, we need to know the shape. We need to know when is p hat normal. Well, for mean, it's a little confusing. For mean, if the population normal, then x bar is normal. If not, we got to use the central limit theorem. For proportion, there is just one rule that you got to check. Or really one rule, 2 parts. N times p has to be at least 10, and n times 1 minus p has to be at least 10. If both of those are true, what that tells us is that p hat follows a normal distribution. You must check both. Big thing that people mess up is the symbol for p versus p hat. So that's it. Now it's basically doing very similar examples to what we just did with proportion instead of mean. So we're going to do one together, and then you are going to do it. Okay. Here is the example that we are going to do. A mail order company advertises that it ships 90% of its orders within 3 working days. You select a simple random sample of 100 of the 5,000 orders received in the past week for an audit. The audit reveals that 86 of these orders were shipped within 3 working days. If the company really ships 90% of its orders on time, what is the probability that in a simple random sample of 100 orders, 86% or less would be shipped on time? Okay, so in your homework, you're just going to be asked part A, and you'll have to jump in. What I've done is broken it down a little bit so we know what steps we need to follow. What I would do is start by writing the probability in probability notation. What is the probability that 86% or less would be shipped on time? That is a sample proportion. So we are looking for the probability of a sample proportion of 0.86 or lower. So then, if we need to know something about p hat, we need to know the distribution of p hat. What is the center? What is the shape? What is the spread? Well, the center of the distribution of p hat is going to be the population proportion. The population proportion is the true value. So in this case, the company is claiming that 90% of the orders are shipped on time, which means our center is going to be 0.9, not 90. The spread is going to be the square root of P1 subtract P all over N. So that's going to be 0.9 multiplied by 0.1 over our N is 100. I think it's 0.03. Yeah. And then we need to know, is the distribution normal? So our N times P, or our 100 times 0.9, is 90, which is at least 10. And then our N times 1 subtract P is 100 times 0.1, which is 10, which is at least 10. So is our distribution normal? Yes. Now that we've proven the distribution is normal, found the mean, found the standard deviation, we're almost ready to calculate that probability. Before we do, I do want the notation P hat is normal. The mean of P hat is that 0.9. The standard deviation of that P hat is 0.03. So then finally, we are calculating the probability that P hat is less than or equal to 0.86. On your calculator, is this a normal CDF or an inverse norm problem? Normal CDF or inverse norm? CDF, thank you. Okay, take 30 seconds, put this in your calculator, and compare an answer with the people next to you when you get an answer, please. I got an answer of about 0.09. You agree? Okay. What am I missing here for this to be a perfect answer? Definitely the graph. I didn't give us enough room, but you know to do the graph. So, answer of 0.09. So then the question is, based on the answer to part A, is there convincing evidence that less than 90% of all orders from this company are shipped within 3 working days? We should talk about this probability real quick. If the company is really shipping 90% of the orders on time, if that's really true, and we were to take a whole bunch of samples of size 1, about 9% of the time, 86% or less would be shipped on time. So that's going to happen almost 10% of the time. What is our cutoff in stats for having convincing evidence? What's the same number? When something's rare? 5%. 5%. Bigger than 5%. So is there convincing evidence? No. Questions for me before you all do one on your own? Okay, here's what you're going to do then. Please go. Okay, so there was something that I forgot to tell us to write down. When we talked about this normality check, what some people do is they forget that, and for P hat, they use the central limit theorem. So they say, my sample's bigger than 30. Distribution's normal. That's not the case. So what I want you to write down is that there is no central limit. Oh, it's frozen. Thanks. There we go. That's where I wanted us to write it. So we talked about these two inequalities. Those have to be checked. So we can't skip the inequalities by using the central limit theorem. There is no central limit theorem for P hat. The central limit theorem, so sample being greater than 30, only applies to X bar. Only applies to sample mean, that's it. So please don't ever use the central limit theorem for anything else, only sample mean. Next page, which is this one. In the other class, what they had the most trouble with was the probability notation. So what I want you to do in your group is take a minute or two, read the problem, and just try to come up with probability notation. We will then come back together, go over that before we do the calculations. Okay, let's talk and see if we came up with the correct probability notation. A pollster believes that 20% of the voters in a certain area favor a bond issue. If 64 voters are randomly sampled from the large population of voters in the area, approximate the probability that the sampled fraction of voters favoring the bond issue will not differ from the true fraction by more than 0.06. Okay, I'm going to start with doing some labeling. What is this 20% if we were to attach a symbol to it? Okay, that's going to be our population proportion. 64 voters is our N. Okay, so approximate the probability that the sampled fraction of voters is a p-hat situation, it's a sample proportion. In my last class, I had some people in their probability notation that has numbers bigger than 1. Remember, proportion is always between 0 and 1. So if you have numbers bigger than 1 or smaller than 0, that's a problem. Bond issue will not differ from the true fraction by more than 0.06. True fraction is that 0.2. So we want to find the probability of being within 0.06 of that 0.2. So visual a little bit. If we have 0.2, 0.06 away is 0.14 and 0.26. We don't want to differ by more than that. We want to be within 0.06 on either side of that 0.2. So writing it out symbolically, I would have taken 0.2 and subtracted 0.06 to find a lower bound. And then I would have taken 0.2 and added 0.06 to find an upper bound. So we want to know the probability of finding a p-hat between 0.14 and 0.26. That's what you're looking for. So at this point, I'm going to leave you here. You're going to need to figure out all this stuff about p-hat. Please act like this is a quiz or a test question and do everything fully. And then when you have an answer, let me know and I will come take a look at it. Good luck. What I have written in black is the work that, oh, you can't see this. Okay, what I have written in black is the rest of the work. You should have calculated the mean, calculated the standard deviation, shown that the work is normal. What I expect is that some of us forgot to actually write that in a line. Hopefully we drew a figure. And we should have seen our answer is going to be pretty big. We get an answer of 0.77. This is what your homework is going to be on, just proportion. But your quiz next week on Wednesday will have proportion and mean on it. How did that one go? It went okay? Okay, I need you to write down this note somewhere. It's probably better on the previous page where we wrote down those 3 properties.